to settings which are not captured by our triptych on A1 and A2, but systems which kind of cannot capture it in that framework, in that there are additional symmetries around. And let's begin this discussion with a kind of, if you will, a case study. That was actually the way how it all started. And we were looking at the following. So here's our old friend again. I mean, normal, disordered, chaotic, ergodic piece of metal. But now we change the rules of the game by attaching it to a superconductor.
Mike,
yes, sorry. So superconductor. Now, and we look at the universe from the perspective of this piece of metal. So particles inside will, kind of notice the superconductor via some boundary condition. Yeah. So this is being a superconductor. We have now to upgrade our Hamiltonian to a Markov Hamiltonian, which allows for the presence of an order parameter. That's we've seen that we can introduce a typical particle hole structure by including here a normal Hamiltonian, particle Hamiltonian. Then they tell us that we have to put here minus H transpose on any basis, and we have here an order parameter sitting. And this is the emission joint. And I do not assume any spin singlet or so symmetry, so this is the most generic superconductor one can imagine, and in my model here, which simply means that delta is an antisymmetric matrix. There is no spin structure around here. Spin rotation symmetry could be broken. So delta has to be minus delta transpose. Just to remind you where that comes from. This is an auxiliary structure which you usually get from some second quantized representation. I mean, you've all seen that. And the way the order parameter enters in a second quantized framework is like such. I mean, you have a single particle basis, and then you write something like that in the Hamiltonian. And these are fermion operators which anticommute, and that means that delta must also anticommute. And that's all we can say. Yeah? If there is spin around and you have a spin singlet structure, then things change, but so far it's good. Just so. All right. Now, again, we anticipate that we will want to characterize the physics of our system in terms of green functions, and the green functions now include this Hamiltonian. So we write down the Gorkov green function. Plus minus h. Epsilon plus h transpose minus delta z. Okay, inverse. Good. And now, yeah, we have to set ourselves an exercise on. Naturally, one thing we can do is we look again at the average density of states. We have done that before, so let's do it again. Yeah? Average single particle density of states in the normal method. And keep in mind, it used to be a boring quantity. I mean, in the normal method there was not much to say about single particle density of states. It became interesting the moment we considered correlations between density of states. So let's see what's going on here.
Do you have a table of determinant in the definition? 1 over determinant of...
What?
So this Green's function, do you have something like 1 over determinant of
no,
h?
Just
Because G is inverse of this H operator. So when you invert this matrix, you need to have determinants. So you are inverting this H to get G plus.
See, this is a Hamiltonian.
Yes.
And my green function is nothing other than what it always was, E plus minus Hamiltonian.
To the minus 1.
Yes.
So when you invert a matrix, generally there is some determinant.
Yeah, but I have
Minus
my
one on
actual-
the matrix.
There's
Oh,
some
in the
minus-
definition of?
Yes, it's
Okay.
I haven't invert. Actually, I will not invert. But what we do is, I mean, we look at the dots inside, which is rho equals 1 over pi, well, you go with this, right? Imaginary part trace of G plus of epsilon. And now there's a whole structure around that means that we should have here sigma 3, I mean, sigma 3 being a Pauli matrix in this case, 1 minus 1. Okay, so how do we get this under control? Before we do any calculations, let's again start drawing pictures, right, and see what's happening. And the situation is now I magnify the piece. I take a portion of this, and we are sitting here at some point x. And taking the trace means, of course, taking the x diagonal elements of this piece. So we start drawing Feynman paths, right? And remember, before the situation, before we had the superconductor, was we can draw paths, and then there was some purity scattering going on. But we argued that any non-trivial path will pick up in essentially a random phase, and that phase tends to randomize to 0. So the average density of states, we didn't have any extended macroscopically extended path contributing to it in the Feynman path picture. That was in a normal math. But now we can start playing new games. And what can happen is the following. So you're an electron, you start out your journey and you propagate, and at some point you hit the superconductor. Okay? Now at the superconductor you have a choice to get converted into a hole. And that's now the new element. Yeah, technically you propagate under this block. Normal. At the interface you can get scattered by this order parameter into this sector. Andreev scatter, right? Okay? So now you have become a hole. And let me mark it. Now, the hole is essentially a missing electron, by and large. And that means that somehow, when you imagine you pick up here a positive action, what you do here is you pick up the negative action, I mean the missing electron action. Yeah? So what we can do now is we can go back to this point, and here propagate along this path back to the superconductor. And what we realize now is that along this leg, the dynamical phase will cancel against the dynamical leg action picked up here to a large extent. So what we get here is something very similar to our diffusion that we had before, yeah? This particle mode propagator. So we do this, and then get converted back to a particle, and complete our job. And that is a phase coherent contribution to the density of states, or to the average density of states. And, so what you imagine here, I mean, if you compare to our worms and all that what we had before, this is essentially, I mean, an object which before, in the normal method, we had only at the level of the two-particle plane function. It appears here already on the level of the one-particle function. Okay? So that's the first indication that there's something, new stuff is going on. Now let me make what I just said, let me make it a bit more quantitative. I mean, and to this end, we just imagine taking a cut here, and we just look at these two, I mean, the analytic expression corresponding to these legs. Okay? So what we have there is essentially, we have here two amplitudes, I mean, plus amplitude, minus. And what is plus? Plus is a propagator to propagate 2 point x prime, let's say here's x prime, under the particle sector of the green function. Yeah? So x prime 1 over epsilon plus minus h to x. And I can call this g plus of mu x prime x, and epsilon. Just the definition. Yeah? Now, what is the minus? The minus vector. Minus is, we go to x prime 1 over epsilon plus h transpose x. Yeah, it's the inverse of this block down here. Okay. So now let's massage this a little bit. We can exchange the indices and undo the transposition. So that is equal to x 1 over epsilon plus h x prime. Okay. And what we can also do is we can pull out the minus sign. So then we have minus epsilon plus minus h. Yeah? And finally notice that this is equal to minus x prime 1 over minus epsilon plus I delta minus h x complex conjugate. And that here is epsilon plus I delta minus h. So this little calculation, expresses what I just said in formulas. It means that the plus amplitude equals the complex conjugate of the minus amplitude. So there is a cancellation of phases, which becomes perfect in the limit epsilon going to 0. Yeah? Epsilon spoils this. This epsilon asymmetry simply has to do with the fact that Andreev scattering scatters a particle of energy epsilon to a whole of energy minus epsilon, and only if you go to the Fermi surface, they become, in a way, degenerate. Yeah, so we have quantum interference now already on the level of the single particle plane function. And now we can suppose we modeled this guy here, the normal matter, by a random matrix. Just one thing. Then we could start now using the same words again as before. We would argue that the product of these two amplitudes gives us something like 1 over energy difference, and there is a singularity in the limit energy difference going to 0. So we encounter phenomena similar to those discussed before, but now on the level of the single particle plane function. Yeah?
What went to 0 there?
Huh?
What went to 0 there?
No, nothing so far. I'm just saying that in the limit epsilon going to 0, they are mutually complex conjugate. And the phase cancellation gets perfect.
I see, okay.
So from that, we anticipate that if we now say, start playing our games, average over disorder and so on, such a propagator here will diverge as 1 over epsilon.
You multiply them together.
Yeah, that's what's happening here. In this lowest order perturbation theory. Yeah.
Is the x prime and x are switched, or in your last expression, x prime and x are switched, or is it?
It's okay, isn't it? I just use that a matrix element because the other matrix element. Yeah. If you have x operator x prime equals x prime x, and everything here is admission except for this edit.
Yeah, so you have the minus sign and the complex conjugate between the plus and the minus expression?
Yeah, the minus sign came, but the minus is not of much.
No. Yeah, just if the phases cancel, then I thought we would have to have like plus the phase and minus the phase. We have plus the phase and minus complex conjugate.
No. The minus is corresponds. Suppose we write this here as e to the I phi, yeah, the phase, and this would be here minus e to the minus I phi.
The minus sign doesn't.
The minus is actually it's something to do with if it helps weak localization or weak anti-localization. It's not, but yeah. Yeah.
So do you have? I missed the first part. Do you have a superconductor normal on the left side, or?
Yeah, I have a superconductor here and normal here.
Right, so should I think of this as a just proximity, like contribution
Yes,
proximity?
it's right. There is no stable proximity amplitude here because time reversal invariance is broken. So I will not get a proximity gap here.
Because what?
It's time reversal invariant. This is a time reversal non-invariant system I'm looking at. I don't have time reversal invariant. But if there was time reversal invariant, this would be the germ from which the proximity effect
Right, like
flows
first
out. I mean, proximity effect is nothing but a non-perturbative accumulation of these guys.
I'm just like confused when I undo the transpose. Don't I get the complex conjugations? Because
no, I don't think so. The transpose is where is the transpose here?
yeah, you
That is
undo-
what I'm using is that say A. Okay, I mean.
Let's say I have some V dagger A V, like V dagger A U, and V and U are some vectors, and then if I do the transpose, then I get the complex conjugations.
No,
Right.
Which of those two expressions are equal to which of the two expressions below? Like,
They're all equal.
Equal.
okay, the same.
And here what I'm doing here is that this is by definition A x prime, which is A transpose x prime x,
Yeah.
which then equals x prime A transpose.
But you have some complex numbers.
Yeah, but they are invariant in the transposition.
The transposition happens only in the first step. Then he's just doing definition.
Okay, sort this out. I draw my next picture, which will take much longer. So, to give you a hint at this being just the first part of the story, much more complicated, let me push my limits and draw another picture. So I'm rotating the whole story 90 degrees. Here's a superconductor. And no. Like this. That. This. Ah. Okay. And now we can do something. We go this way. Now we become a hole. The hole does this. Becomes the particle. Okay. And that shows that you have these nonlinear interactions. It's already on the level of the single particle density of six, right? We start out somewhere here. I will not draw the arrows. I will propagate. Everything is phase coherent. I mean, everywhere phase cancellation. And that's similar to one of these nonlinear interactions, but now again on the level of the single particle spin function instead of two. No?
Can you put the direction of arrows at least? You don't
Do it yourself. I mean, you go in one way. I mean, just one direction. Yeah.
So last lecture you told that in this situation you're supposed to first solve the Zadel equation, find non-trivial solution.
No, there's no proximity effect here. Tabular is broken.
And this is, so what?
Yeah, but Zadel equation, it's like a superconductor in a magnetic field.
But you didn't feel superconductivity.
No?
You didn't feel superconductivity.
No, but I have no time reversal invariance here, so you can think of an ordinary superconductor and I apply a magnetic field in here.
Okay.
And then I have such an Hamiltonian, the time reversal symmetry is broken here. H is not equal to H transpose. And then I have, I mean, it's class D, I don't have a proximity effect. Yeah. I mean, really. Yeah.
Maybe a related question. So what I don't understand is, why do you need to, like, for the first part, before you move on, why do you need this more complicated structure? Why not ask the question, I'm inside superconductor, here's my Green's function, and I'm just going to compute inside superconductor. Why do I need
I don't want to have a quasi-particle gap around.
I see.
So Alex's question is about this. If I have time reversal invariance present, notice here, now I'm getting back to your arrows. The arrows are all in one direction here. Yeah. If time reversal invariance is present, then H equals H transpose, and then I get the following structure. I propagate here, and I propagate the same way back. And suppose here is another superconductor, I mean, just for artistic purposes, and my first contribution will be this. Same path back. And that gives you a much higher amplitude. And now you can start building up here, I mean, with localization type corrections. And if you sum them up, then they give you a solid gap. But not in the symmetry class.
So the only role of superconductor is to kill U1, to kill charge conservation.
Yeah. No, well,
But you're doing it at the boundaries.
yes. I mean, the essential. This is the essential story. I mean, this is the one and only thing that's important. You have the superconductor Green function that is undecided. It cannot make up its mind. It's a retarded and an advanced Green function at the same time, and they're
Right, but in the picture that you draw is not that Green's function. In the picture you draw, delta is a function of x.
no, delta is a boundary operator here.
Okay, so it's only sitting there.
Yeah,
That's what I mean. It's a theta function of the function of x, let's say. But somehow you're saying that doesn't. Okay, when you perturb, when you expand in delta, that's what you.
Yeah, I mean, look, this is only for, if you want pedagogical purposes. I want to show you that there's something going on. I'm not doing any calculation. Yeah. Good. So what are the take-home messages from here? We have quantum interference at level of a single Green function, and we anticipate singularities in the limit epsilon going to 0. Why do we have to have these singularities? I mean, remember in our earlier discussion of random matrix theory, these singularities had something to do with level repulsion, or they were the precursors of level repulsion in the spectrum, right? And here we observe similar things going on already on the level of the single particle Green function, and that the physical origin behind this is the following. Suppose you have a look at the spectrum of a superconductor. So here's the Fermi level if you want. And here we have our epsilon. Okay? Now the spectrum of a superconductor is particle hole symmetric. It's inversion symmetric around this point. And at the same time, this is a random spectrum, so we expect something like level repulsion out here, but everything is symmetric with respect to 0, right? Now the moment a level starts to get down to 0, so limit epsilon to 0, its mirror will come from the other side and they see each other. And they typically they will repel, sometimes even attract. And so if you now average over this, you have to have level repulsion already on the level of the single particle Green function, unlike in an ordinary metallic spectrum where there is no preferred mirror point. Yeah? And indeed, if you write down an RMT model for the system, which you can do, and you work out the density of states in RMT, then you find that rho of epsilon equals 1 over delta times 1 plus sine S over S. So there is our sine kernel over S is already appearing here at the level of the single particle density of states. And there is a quantum interference anomaly in the band center.
So this is in the middle of a semicircle.
In the middle of the semicircle, exactly, on level spacing scales. And notice that if, yeah, notice nothing. I mean, it's just fine as always. Yeah? Right.
Is it minus or plus?
Plus. That is class B here, and I'm coming to that. There are 4 superconductor symmetry classes, and in one of them there is a plus sign here, which is somewhat counterintuitive. So you have weak anti-localization and level attraction. Which this plus, by the way, I mean just anecdotically, is responsible for the fact that in current Majorana experiments it is so hard to discriminate between real Majoranas at the band center and disorder effects. Levels really want to go down to 0 energy, and it's very hard to confuse them with real Majorana caveats. Such remark.
So where is
Yeah.
the superconducting gap here?
So the gap is
Totally different energies, much larger energy scale, right?
You're in a normal region, right?
oh there's a gap here.
Yeah. But S is much
But
smaller.
this-
S is much smaller than
Yeah,
the
S
gap.
is
Much smaller than the gap.
sure. S is okay. But there is no gap in the normal metal. There is no proximity effect
So this is the spectrum in the normal metal?
in the normal metal.
Well, in the whole system, because the superconductor has nothing at its energy scale, right?
Yeah, but in a bulk superconductor, depending
It's
on what it
zero,
is, I mean, there is of course a huge quantum particle gap.
Right.
But not, no, here you have the density of states
This is
here quite
gapless.
finite. You have a metallic density of states in the normal metal with a weak quantum anomaly in the middle.
Right. But if you included the superconductor and looked on this energy scale, you wouldn't get any more states because the superconductor has a gap.
Yeah, no, yeah, it's just
So
all
it's the full density of states.
And shouldn't there be a distance from the superconductor involved somehow, like if I go further away from the...
Absolutely, this is random matrix regime. So I'm playing again the same games. I'm on energies much below the Thomas energy.
I see.
If this is an infinite
Oh, I
map,
see, I see.
then you have non-ergodic and this effect will
Will
die out.
feel it everywhere.
Yeah.
Okay.
That's a good question.
Yes.
So this is now for the model that you were originally discussing, or the one with time reverse distribution?
That is with time without
With
this.
time.
That would be different. You just remove the transpose.
No, but the density of states. Is
Oh, that is for the time without the non-invariant one.
A.
No? So let's do what? All this suggests that there's symmetry-wise something going on. I mean, something beyond what we've been doing so far. So let's take a brief look at the system from the perspective of the first of our 5 lectures, where we discussed anti-unitary symmetries on that, and observe the following. If you look at this Hamiltonian, then you notice it has the following symmetry. If you transpose the Hamiltonian and conjugate with sigma 1, polymatric sigma 1, right? You get minus the Hamiltonian. That is the, another way of saying that the blocks you have the particular structure is indicated. No? Okay.
Which space sigma is?
Here.
Particle space.
Okay. Okay, doesn't look very inviting, or maybe, well, it's like this. But now let's play the following game. Let's introduce an operator k, which is almost our Hamiltonian, but we conjugate by Pauli matrix sigma 1 to the power 1 half. Yeah? And here a similarity transformation. So that is up to some similarity transformation. It's the same Hamiltonian, nothing much. It's just a change of basis. This change of basis is actually sometimes called the Majorana basis, but it's just a word. I mean, now if you plug this in here, then you find that K transpose equals minus K. Okay? Minus K. And we can express this in the following way. We can say Tk, T inverse. T is is just complex conjugation, our time reversal operator for, in this case, where it squares to 1, equals minus K. Where before we had plus K in the normal metal, right? So that tells us that anti-unitary symmetries in real life systems sometimes do not leave the Hamiltonian invalid, but they, in fact, they change the sign.
How did you get that?
This here?
Oh, from there.
This time reversal is a complex conjugation. I'm just telling you that complex conjugation, if you mind saying complex conjugation is the same as transposition because it's addition.
It's just a bit confusing because K beforehand was.
Yeah, I know.
Complex
Give it
conjugation.
another name. I mean, whatever. it will not appear anymore. This is our first and last time we made a K. Okay, good. Now we can crank our machine and say, aha, this is the generator of our time evolution. Yeah, okay, and what it is, time evolution is now generated by an anti-symmetric matrix. So what is the symmetric space? Question? No? No? Orthogonal. Cool. So we learned that U, which is X, I was cheating, it's in fact another time that K appears. Is element of O to N, and this is the symmetric space D to N in Cartan's notation, plus D symmetry. Yeah? So we have another symmetric space. Okay, so that's all for the moment about the superconductor. The essential observation here is that anti-unisymmetries, where before we have been considering commutative scenarios, they also anti-commute with the Hamiltonian, and you get non-empty physics. And that now immediately leads to the tenfold classification. Because
So what's this D2? So the U is in the orthogonal, is an element of the orthogonal group, and then D2 is
D2n is in the Cartan notation. D2n is a rank 2n orthogonal group. It's a symmetric space.
But then you just isn't O2.
Oh,
capital.
capital.
But is that not the same as ON with n twice as large? I mean, is that?
Yeah, but On is a symmetric space, and its name is D.
Oh.
Somebody called it D. I mean, somebody called it. But it's nothing other than the orthogonal group. Yeah, you're right. So you have two different ways of classifying symmetries, and going beyond this is referred to. There is the intellectually appealing way, and somewhat more high-powered way, where you argue that this Nambu representation is, I mean, behind it there sits a Fock-space representation of fermions, and then you work in Fock-space, and you never have to talk about anti-commuting symmetries. That's one way. I'm presenting to you the more pedestrian, in a way, more cost-efficient way of classifying them, which goes like this. So let's anticipate 10 different situations by doing the following. We introduce a time reversal operation, which, I mean, like what we had before, namely some unitary matrix, which can be the unit matrix or Pauli matrix, times complex conjugation. And then we have, not this case, might be head. Yeah, it's a head here. There's no head here. Then we say that our Hamiltonian has a time reversal symmetry when we have the following situation: H equals U transpose dagger H complex conjugate. Namely, this is K without head acting U. All right, so that was its time reversal. Now we introduce a second operation. We call it charge conjugation. It's just a name tag. And there is another unitary matrix. I mean, again, could be something like unit matrix, or it's an anti-unitary. So there is no up to unitary equivalence. We don't have too many choices. And same complex conjugation. And we call the Hamiltonian charge conjugation invariant. It's just a definition. It's a name. When H behaves under this operation is a minus. No?
Sorry, what do you get from
C.
What is UC?
Some matrix. I mean, either the unit matrix or Pauli matrix. I mean, C being an anti-unitary has again the option it can square to 1 or square to minus 1. I mean, the same, everything that we said about T applies to C just the same. Yeah? So for UC up to unitary equivalence, we can write down a unit matrix and this funny matrix, Pauli matrix, which we had before. That's basically exhausting it. And that gets me to the following.
What kind of symbol is this epsilon underneath?
Yeah, so it's my calligraphic C. Like this is a calligraphic tau. No, that's a tau. That's what it is. So remember we had these two options. T squared could square to 1 or minus 1. And correspondingly, we introduced for tau the notation 0 if there was no time reversal around. And this we call tau 1, and this we call tau minus 1. Say time reversal invariant operator, if t squares to minus 1, we call it tau minus 1 tau, right? Now we can play the same game with C. The C squared can be either 1 or minus 1. And our Hamiltonian can have no particle Hall symmetry. I mean, it just doesn't know about it, normal metal. Or it can commute with C in the situation squares to 1, in which case we call C1, and this C minus 1. So we immediately see we get 9 different options. 9 different situations under T symmetry, right? I mean, you give me a Hamiltonian and I ask you, is it T invariant, yes or no? Is it charge conjugation invariant, yes or no? And if yes, which situation do we have? 9 options. Yeah.
I don't understand. Are you saying that for all Hamiltonians, these above relations on the tau and the C hold? Or is that one of these options on the table?
One of these, yeah.
So it's the one where
Yes.
C is minus 1 and
I mean, look, remember in the first lecture when I was telling you about anti-unitaries, I always insisted that we need not to consider time reversal, could be any anti-unitary operation. That's having this here in mind. If any anti-unitary operator, you can by multiplying it with a unitary, you can bring it into an involuntary form.
I'm fine with your writing it in this board. I'm asking about the stuff on the right side of the board. You're saying that the Hamiltonian is exactly equal to, well, I think of a minus sign when I do charge conjugation,
Yes.
and no minus sign when I do time reversal. Is that a general statement, or is that one of these classes?
No, it can have charge conjugations in no time reversal.
He's asking you to review the meaning of those statements.
By definition, we call the Hamiltonian time reversal invariant if this equation holds. By definition,
And that would be one of the two at the bottom.
That's the 2 bottom ones.
Yeah. There's 2 options.
Either one, then you ask whether it's
Then you ask that question.
Are there now statements being made or questions asked?
You say it.
No, I just have to figure out if there's a statement made, I shut up. And if there's a question, I
I'm
say
still
back on
questioning,
that.
please.
Huh?
Could you say what they just said, but I didn't understand?
No, I cannot because.
So the answer is yes or no at the top here.
Yes,
It either satisfies that or not.
yes,
Not is the 0,
yes,
and yes is either the 1 or the minus 1.
exactly.
Okay.
That was a good statement, yeah. Yeah.
I had a question about a statement you made in your first lecture. Was
Yeah.
it that if you have this Hilbert space, there's this space of anti-unitaries and
Yeah.
unitaries, and there's one thing that's basically generates all anti-unitary
Yeah.
operations.
Exactly.
And so here so these two are related somehow, that, right? Because in this Hilbert space now you have a second unitary operation, or anti-unitary operation, right? Or don't you?
No, they belong to the same equivalence class.
Uh-huh.
I mean, you can see it quite explicitly here. Our charge conjugation is our good old complex
Right.
conjugation, but there's a unitary multiplier.
Right.
The new aspect appearing here is a new question asked. Is your Hamiltonian, does it anticommute or not?
Yes.
I'm asking a new question about an operator.
No, I understand. But then T and C are somehow related. They are.
Yeah. You'll see it in a second when I combine them.
Okay.
That's a very good point. I mean, 9 options. Can we agree on that? Yeah. But there are 10 symmetry classes, so where's the missing one? And the answer to that lies in a third symmetry operation, S. And S is simply T and C combined. I can do that, right? I mean, we know particles, and you have 2 anti-unitaries, you like to combine them. Now, do we get any new information from here? I mean, if T holds, I mean, if or C holds, then we will not get any kind of new information from this operation. But if what can happen is that you have neither T nor C, but still S. Yeah. And then again, you have an option commute and not commute. Okay. I mean, that's our.
But that's the third unitary operation.
Yes. No, that one here is unitary. It's unitary, and you see it quite explicitly. It's unitary, and so let's just work it out. What it does, I mean, H under S. What will happen? So it transforms to, I don't know. I mean, S and T, tau applied to H. So let's first do tau. Then we get that's tau. U transpose dagger H complex conjugate U transpose. And then we apply S to the whole package.
Why S?
Yeah. So we apply C to this entire thing. And well, we have C. It's this here. So we get a minus sign U C dagger. Oops. U C dagger. And now we have to take the transpose of this here. Like here, yeah. Or complex conjugate, same thing. So U T transpose H, the same H star complex conjugate, U T complex conjugate U C. Okay. And these here, these guys here are unitary matrices. These are unitary matrices. So this is unitary. And that is exactly what has been alluded to. These guys are unitarily equivalent. However, mind the minus sign. What we are asking now is that H, in a way, should anticommute with a unitary matrix. Anticommute, not commute. And that's a chiral symmetry. That's what is called chiral symmetry. So this here is, and we are coming to that. I mean, yeah.
So, so someone gives us a Hamiltonian,
yes.
right? And I find a unitary operation that that basically anticommutes with the Hamiltonian. Yes. Is that my S? Because
then exactly. Then you are in a chiral setting, in the chiral symmetry, and you
but then no reason to call it a tau and a C.
No. There's no. I'm not telling that. I'm just trying to do the counting here. And I'm trying to make, I mean, a few logically, hopefully consistent statements. And one of them is that here in this nil-nil scenario, you can still have 2 options under S.
But then tau and C are not really defined, right? I mean, if it's not, I mean, tau might be defined because there's the physical reasons why tau should be defined.
No, they are
but
defined.
something like C is not. Oh, the charge conjugation is. So, if there is no symmetry of H or antisymmetry of H under some operations called tau and C, how do I compose such operations and call it S? That's my question.
No, the operation exists.
The operation exists, yes.
The Hamiltonian.
Yeah, the operation is just is a statement about the Hilbert space.
I mean, you could have an antiferromagnet in the L state. It doesn't
No, I
reversible
understand. So you need
translation.
some extra physical input. You just, it's not like there exists UC and UT that does this.
No,
I mean,
by definition, the tau of H is UTH star UT.
And you can always perform this operation, just you don't know if it's equal to h or not. And in this case, it's not equal to h, but you can still perform it and perform C, and then see if this result was
Then
like
how
two
would
operations.
C be defined?
The same way, C is minus.
I understand, but how is C defined? Tau is defined by time reversal, so there's some.
T is time reversal, C is charge conjugation.
Okay.
You could have a Hamiltonian which is not invariant under either alone, but it is invariant under both.
Okay.
It's not really invariant, it gives you -1.
The interesting thing to watch out for. I mean, what is interesting here? This UT and UC are whatever. Very interesting is this minus sign. And in the combined operation, I asked for a Hamiltonian. I mean, that makes its way down to this minus sign, and then we have a Hamiltonian anticommutative with something that is unitary, and that definitely gives us a new structure. Yeah.
I'm not sure whether for the up there you will find S as tau times C, and the down there you will find the C times C.
Yeah, right. No, yes. Let's define the other way around. Yeah.
The right board is clear to me. What's the relation between the center board and the right board? What's written on the center board and what's written on the right?
This board,
right.
That
So,
board?
right. So, you, for example, the last statement you make is TKT
Yes.
minus K.
Yeah, that is
okay.
That is a C invariant statement.
That's the C invariant?
Yes, C invariant. I mean, H equals unitary matrix transpose another unitary matrix.
So you're saying at the level of K, you just means anticommutative.
In the level of K, I mean, here our K, think of it as H, and our UC in this case is a unit matrix. I've conjugated it away, and in this case I'm asking for anticommutativeness.
So T doesn't mean time reversal, it just means anti-unitary operator.
Yes, it's right, complex conjugation. I went to a representation where my T squares to 1, and I'm anticommutative, so I have a particular type of charge conjugation symmetry. And no time reversal symmetry.
No time.
So we are here in this case, we are here. Yeah, that is class D. Yeah.
At the first lecture you said that if we have a unitary class, right, and we have only one anti-unitary member, we can get all the anti-unitaries, right?
Yeah.
So C and T are both anti-unitary.
Yes.
That means I can find a unitary transformation act
it's here, yeah.
one of them. I can take, let's say, T and a unitary transformation and define C using it?
Yes, absolutely. But only these operators. The question, the essential point is here I'm asking, are you invariant?
Yeah.
Or are, yeah. Oh, no, absolutely right. Yes.
What is the smallest Hilbert space that I need to realize all of these?
All of these. So you want to be somewhere down here? 4 times 4, I would say.
For matrices.
In terms of matrix, I can write you.
All 10.
You want to be time relevant man? So, yes,
all 10.
So, I mean, in principle, could I pick up more anti-unitary symmetries, or does that not work because
no, there's only one. There's anti-unitary symmetry. There's essentially only one. And then I can ask the question: compute or not compute?
In the first lecture, you were also talking about spin. So there are
Yes.
3 classes actually.
No.
Time.
Spin is if you have spin, then you can play these games. You can play nothing more. I mean, you give me any Hilbert space.
So it doesn't give any extra.
No,
classes?
nothing. No. You give me any Hilbert space you want. I mean, no matter what. I go to irreducible representation and then I check this table, and I will wind up in one of 10 scenarios and situations.
But I mean, if you just give it a general Hilbert space, you can't really define a C and top, right? You see what I mean? I mean, there's
No, I can always do that.
well, you can't do that unless you have those symmetries. You see what I mean?
No.
I mean that.
Operations, whether the symmetry is there.
Why not? I mean.
Well, then I would be defining some random UT and UC.
Yeah, but up to unitary equivalence, they are all the same. then you can ask, I mean, we can play this game and you do it in one room and I do it in another room, we get answers, but these answers would be unitarily equivalent if we don't do a mistake.
So the way to go, the algorithm would be take a Hilbert space and someone has given me Hamiltonian and some constraints on the Hamiltonian. Then I go and start checking my Hamiltonian for, you know, are there unitary symmetries, anti-unitary symmetries that either commute or anti-commute? And if I don't find any, can I find a unitary symmetry that anti-commutes?
Yes.
Right. I see. And then when if I get a unitary symmetry that anti-commutes,
yeah.
There's no way for me to actually make up a time reversal and charge computation from it.
No, if you don't have any other symmetries, no, then you are in a, we call it symmetry class A3. It's just anti-commutativeness with unitary.
With some unitary operation.
Yeah.
I see.
With.
What if there's more than
I mean, no, hang on. Yeah, no, you're right, yes, indeed, there's one.
Oh, and this is unique because if I find some other unitary transformation that does.
Up to unitary equivalence. In most cases, you will never ask this question because, I mean, in real life, they give you in Hilbert space.
Yeah, yeah, that I understand.
It always comes
but
later.
algorithmically, it's confusing.
Could I cook up a situation where I hit the Hamiltonian with a certain operation and I get the same Hamiltonian back with an arbitrary phase instead of plus or minus 1? Spirit of projective
no. Can you, because these are involutions, these operations. I think you might have a trouble with that.
Right. Has to square to 1.
Yeah, something. I guess you
would just prove that in the first. You addressed that in the first lecture, right?
Yeah.
You showed it. You first it was a phase, and then you showed it.
Yeah, exactly. Yeah, they are involute. Yeah.
So I was wondering, so like time reversal and particle Hall or charge conjugation have like pretty clear physical kind of rationalization. So like all the various classes here have like clear examples, but the one that's like 0, 0, but has the chiral operation.
Yeah.
What is like? Is there like a quick way to think of have some intuition for that?
Yes. First of all, I dare to object. I mean, it's maximally confusing the way people use the words charge conjugation, and never trust them. I mean, everybody has his own convention in mind, was socialized in different ways. I have met so many people who call it one thing we would call time reversal, they call it charge conjugation. It's total mess. So my way of approaching it is take a problem and sort it out yourself and then give them labels. Having said that, say the chiral situation, right? In fact, there are 3 distinct chiral symmetry classes because if you have S symmetry, you can still have T, and the canonical realizations are, for example, I mean, really particle hole antisymmetry in Dirac operators. Yeah? It's a very, very good case of particle hole invariance. Another one, which John Jocker has been talking about, are sublattice symmetries. And that was my next case study. I wanted to go back to that. Yeah, sublattice is chiral.
Sushi for Heger or something?
Huh?
Like sushi for Heger instead of?
Simpler. I mean, you take a bipartite lattice with purely off-diagonal. I mean, like graphene in the absence of. And I guess what I want to say is this. I mean, there are for each of these symmetries there are good reference systems which come with a lot of physics, which is similar. But then you meet the superconductor, and the superconductor can easily be chiral, and it has the same phenomenology as a system you are used to from a totally different context. I don't know of a unique, clean classification which puts these things into a cage, and often a symmetry which appears in an unfamiliar context. Yeah.
So like for the normal state, you were saying, let's say in graphene you have bipartite lattice with a copy.
Yes.
So that would be chiral.
That's chiral.
What is an example of a superconductor that's chiral?
A class C1 superconductor, that's spin rotation invariant. Okay. If you have
it would help to have some physical. It would help to have some physical examples of each of.
Yeah, I wanted to get there, but we are classifying for half an hour now. I mean, I have lots of examples, but I have our nice discussion.
Go on.
What? No, we have to make a choice. Time is. So, one example, I mean, that was this class B setting I gave you. Now comes another one, which is, which I also quite like, is a chiral symmetry situation. And So now I want to show you how chiral symmetry appears in a very mundane context, I mean the simplest system you can imagine, and at the same time reflects phenomenology which we are familiar to from particle physics. Yeah? So particle physics is also quintessentially chiral symmetric in massless limits. And that's another case study. So that's one which I think John has talked about it, right? Sublattice system. So what we consider is a bipartite lattice. So a lattice that can be arranged in this way into two nested sublattices. And I assume a situation where the Hamiltonian is purely hopping. I mean, there is no on-site matrix elements, in which case the Hamiltonian can be written as x dagger in a sublattice decomposition. Yeah, it always hops you from. And now we get immediately our chiral symmetry because we can define tau 3 as 1 minus 1 in the sublattice spaces. So an operator that multiplies all circles with minus 1 and leaves the crosses untouched. And this operation will anticommute with the Hamiltonian. Yeah, so it's a unitary operator, anticommutes with H, chiral symmetry. Now what are the consequences? The consequences are very similar to what we discussed before in our superconductor example. We can play the same game, and I will not do it in view of the time. But this is again, I mean, this is zooming out now. I mean, this is a portion of our system. We could again compute the density of states, huh? And then we observe that if we propagate in our system and decide to propagate back along the same path, the two phases cancel out against each other. And it's done, the calculation that shows you is done exactly the same way as we did here for the class B. We write down the green function. We observe that the green function, that the Hamiltonian changes sign under conjugation with this B scan. We can, in the very same way we deduce this phase cancellation. I guess I don't need to show this, right? It's a similar calculation. It's in the notes, I mean, you can see that. So there is, again, the same works. This symmetry introduces quantum interference at the level of the single particle green function. And another thing, we can ask ourselves, what is the symmetric space generated by this Hamiltonian? Any suggestion? We've seen it before.
Divided by 2u.
Oh, just look at the Hamiltonian. What now in the time evolution into the IH? What symmetric space would be generated?
U to n divided by 2u.
Yeah, exactly. U to n over un times un, but now with color n, and that's A3 capital N. Before we had, this morning, we had A3 flavor. This is now A3 color. So that is here class, symmetry class A3. Okay, so now let me say very few words, very sketchy, on the construction of the low energy field theory describing this setting. So I just want to, in a way, recapitulate certain steps we took this morning when we constructed the field theory. And what we discover here is kind of interesting. It's quite a bit of structure we can get without much technicality. So suppose we take this Hamiltonian and now we play our games. We write down the Gaussian integral, psi, bar, Hamiltonian psi, and so on, and then start evolution. What kind of structure will we get? So I'm just writing a few compound elements or formulas we had this morning. So the canonical bilinear form we would have is like this: x dagger. psi, psi. And right, these were our, I'm suppressing everything here. There would be flavor indices, color indices, just the structure. And these are two fields, let me give them a label left, right, and here right, left. Like right and left moving fermions, yeah? Just a label. These are independent variables, so I can name them, whatever.
But over here it was sublattice, though, like.
Yeah, they are sublattice.
So you call the two sublattices right?
Yes, I call them left. I mean, you call them here these. My Hamiltonian couples left bars with unbarred lefts. That. Notice that there is a symmetry around. The color symmetry is now, in fact, the product of two groups. Because what I can do is I can transform psi c, left or right, goes to u c psi c, and psi bar c goes to psi bar c inverse. And c is left or right. And u are big matrices, right? In operating in the sublattice space. So we see that there is a symmetry group, which is now a product. U left n times u right n. So we go two independent symmetries, U left. Huh? In the native field. Okay. Now what happens if we, and that is called a Carter symmetry. I mean, or that's one way of putting it. Typical Carter symmetry, and you know it for mass as QCD. And now let's see what happens if we average over disorder. So there is some disorder sitting here, some Gaussian disorder, right? Some random matrix disorder or impurities, and we average over it. Yeah?
L and R are just the sublattices, right?
Huh?
L and R are just the sublattices.
Yes, you can give this, but mind that the order is reversed.
Swap the layers, yeah.
So it's not too helpful to stick too tightly to the sublattice. Just leave them as they are.
Okay, so that reversing is intentional.
Yeah, that's intentional. I want to have this symmetry. I mean, symmetry operating entirely within the left sector. So I have to have here my matrix and here the inverse of the same matrix. So they. Now, if we do a disorder average, so then we obtain the following. There is again our bilinear form: psi bar left, psi left. Yeah. And here we average, we get psi bar right, psi right. We would get a bilinear form of this architecture. But this order. You see it, yeah? So there is some randomness sitting here in the left sector, and then I correlate it with complex conjugate randomness here, so I generate such a bilinear form on the average. Now we play our game again. We bring our fermions to this side. Huh? So we rearrange. So this is what is, I mean, what we did this morning. Psi left, psi left, psi bar right. And we Hubbard-Stratonovich decouple in this set now. Okay? So if we do that, then our Hubbard-Stratonovich field now all of a sudden connects left and right, and it will appear here. So there will, the matrix field, our low energy matrix field will sit here in this sector. So we obtain a structure psi bar left, psi bar right, something like A, let's call it left right, A right left, and here X naught, and here X naught dagger. Psi left, psi right. Oh, psi right, left. Okay. Now, next step would be a mean, such as mean field calculation. Yeah? And what we will find is that there are non-vanishing mean fields popping up here. Mean fields sitting here and here. Yeah? And that phenomenon is known as spontaneous breakdown of chiral symmetry. You may have heard it before. I mean, it's very famous in QCD. It's at large length scales, QCD spontaneously breaks the product chiral symmetry down to a single copy of the Q. But But it's also been discussed in connection with graphenes, and graphenes subject to strong interactions, prone to do that, and disordered systems do it all the time. You get it? I mean that, so on the mean field level, this symmetry is spontaneously broken. We had it here, but on the mean field level it gets broken. So if we have now this mean field sitting here.
So what kind of disorder is this now?
Any disorder.
But there's probably no on-site disorder because that would break.
No on-site disorder. That would break it explicitly.
So this is hopping disorder.
This is hopping disorder. Hopping disorder spontaneously breaks the chiral symmetry on the mean field level. It's gone.
So in the context of graphene, this is just saying you don't independently conserve value k and k prime numbers, you just conserve overall charge.
No, it's more than that. It's more than that. It's in graphene. It has been first of all in graphene it has been discussed in connection with real interactions, and no, the point is that you don't need to hop between the. You don't need to introduce this order that explicitly breaks the symmetry to break it on the mean field level.
Is that then a threshold effect? Or is it arbitrarily weak disorder?
Very good point. The moment your disorder generates you such an imaginary self-energy, like we had, it's there. For real interactions, electron, you have to go to strong interactions and you talk about fine structure, for instance. For disorder, it's there. Right. So. The symmetry gets broken, and if you ask yourself what survives here of the symmetry transformations now are reduced to U left equals U right equals U. So we get from a product symmetry to a single symmetry. Yeah. Okay. So to throw maybe an analogy to you, which just for entertainment purposes. One context I mentioned where this appears is QCD, where say you have in chromodynamic context you have quarks, left and right moving quarks, and they have two indices, the color index, quark color, and flavor index, and they interact with a gauge field, right? With a color gauge field, which is, in a sense, plays the role of our disorder. Now, at large length scales, there is a QCD phase transition, and they strongly bind to composites, which are color singlets. To color white objects, which, however, still have their flavor structure, right? And this happens when a so-called quark condensate appears. That's signature of the chiral phase transition in QCD is appearance of such a condensate, which is none other than this subatomic. Now these composites, which in our context would be here will be our Goldstone soft mode, we see in a second. In QCD they are mesons. So quark anti-quark pairs, color neutral, white, but flavor structure is around. So that's where this nomenclature, color flavor, we have been playing with came from. You can forget this, what I just said. It's just an anecdotal side remark. I'm very briefly.
I have not a question. If this, so if we go back to something like graphene with no interactions, then each individual disorder realization is going to obey this chiral symmetry.
Yes.
And so the phenomenology of an individual system should be chiral symmetric. But somehow if we average it and get the mean field, it's broken.
Yes. And then we get a Goldstone mode, and this Goldstone mode reflects the propagation of particle and retarded advanced particles bound together by this disorder.
But any individual system will not have this Goldstone mode? Because any individual system will still...
That is a very good point. When you say every individual, what you're asking is an individual system self-evolution or not. Now, as long as you talk about generic paths in this final path picture, and don't worry about these random phases. You say I'm one system and I consider all my complicated phases, the symmetry is not broken. But in fact, the fact is that effectively, in an individual system, only these paths propagating along the same trajectory survive. I mean, in this sense, that would get us into the field theory of quantum chaos now. Constructing these theories for given realizations. I'd rather not touch this point. But the poorest answer is for a given realization, no. Yeah.
In mesoscopic samples, as you dial up the size, can you actually see a transition between self-averaging and not? With a very small sample, is it still
so not? I mean, mesoscopic systems are never in a strict sense self-averaging. It's always large fluctuations.
So as you dial up the size, can you see a transition from something which looks like it's pretty much self-average, like it's not very good at self-averaging, to something which is a lot better?
Well, no transition, I don't think of it. Crossover.
Crossover.
Now asking me whether it has to be.
I'm asking,
no,
can you observe this crossover between bad and good self-averaging?
Numerically, you could probably see something like that. I mean, but I'm not aware. I guess I'm not ready to give a halfway intelligent answer to this question. Okay. So now let's push on a little bit in this direction. I mean, not much, but suppose we went on and like this morning. So we would now say, aha, we have here a mean field, and let's give it a name. I mean, so we go to this psi. This is psi bar left, psi bar right, psi right, psi left. Here's x naught, x finger. And here we have now a mean field sitting, I gamma, which imaginary amplitude times the unit matrix, right? So we find a solution of this type. And now we say this is not the only solution, and the way to get other solutions is to subject this symmetry broken mean field to the transformation under the full symmetry group. Again, like in the magnet and everywhere else. So we apply this transformation to that action, and this will then, by construction, reveal the Goldstone in the problem. So if we do that, if we subject this to such a transformation, we get psi bar left, psi bar right, and here I gamma, Q left inverse, Q right, x naught delta, I gamma, Q right inverse, Q left. Psi right, psi left. And these pieces here, the products of these transformations are our Goldstone modes. These are the Goldstone modes in the problem. So let's call these pieces here, let's call this product U. And then we have here U inverse. And these are now, these fields replace, in the Carrel setting, assume now the roles of the Q matrices, which we had this morning. There is no longer this, they play the roles of these guys. So we have a correspondence between symmetry class A3 and color corresponds on the flavor level to the unitary group. I mean, this is a Goldstone manifold unitary group, and that was the symmetric space A sub AN. Good. So we anticipate that the sublattice system, or any system with Carrel in this order, and should be described by a low energy field theory where the fields are unitary matrices. Unitary matrices, yeah. Okay. Now, what is the? Can we guess what would be? Yeah.
In my happy state of ignorance before this lecture, I used to think that you just went along, classified the system according to its symmetries, and then it told you what class it was in.
Yes.
But now there seems to be an ambiguity because like the class and flavor space is not the same as the class in color space. So
what class?
I mean, the target space is A3 in color space and A.
No. We are absolutely on firm ground. I mean, we are dealing with an Hamiltonian which has color symmetry of this type. Right. Now, we anticipate there will be low energy field theory.
Right.
Question is identified. These fields should again take values in a symmetric space of lower rank, in flavor space. And this very sketchy discussion tells you that in the present case, these fields live in the unitary group.
I guess what I'm asking is there a one-to-one mapping from the color space to the flavor symmetry space?
Yes, but it's not, you have to work it out for each of the 10 classes.
Okay.
I think I'm not aware of any halfway comprehensible, I mean, no, there is no, you just have to work it out.
But the 10 pair up into 5 pairs?
Huh?
The 10 pair up into 5 pairs? Or that doesn't have that structure?
No, I don't think there is any system. Well,
There's no structure.
I think Martin Sommer might be differently. He understands structures I don't understand. But
okay.
I never understood any. So you draw 10 of these, and here you have 10, and you stare at them, and I don't understand the system.
Right. But we had before this that AN color space was A3 in flavor space,
yes.
and now it's the other way around.
That's excellent.
It's just a coincidence.
Okay.
That's
okay. The only example.
Yeah, or maybe not in, but.
So you do it again.
Yes, hang on. Maybe
doesn't
not.
always do.
Maybe you can go in a convoluted way, can go back and.
Yeah, if you do it again, that's not going to go back.
Just the other way around. Yeah, perhaps.
But that would pair the 10 up into 5 pairs, right?
I think there's sometimes a factor of 2 that you have because of parasymmetry.
Could also be.
But does it have to do with some, that A3 and A both break time reversal and so they come together?
No, there's, in this case, I think, wouldn't even bring up the notion of time reversal.
Right, but still.
Yeah, still, perhaps, yeah.
How they group together.
Yeah. I have 10 moments. I mean, if you let me, I would just throw a few things at you. I mean, like, I mean, not be rigorous. I just want to flash it and maybe get you interested, perhaps you. So we can, what is the low energy field theory for the unitary group? So what would be a good, I mean, the nonlinear theta model, what we had this morning, but now for the class A3. We are in d dimensions. Now please dictate. No? Constant? Line?
dq?
Yeah.
dq squared? dq?
There is no q, there is
u. Okay, du.
du?
U squared.
U squared. But it should be invariant. I mean,
D vector.
yeah, inverse. That is a good term. Right. Now, assume we have some weak explicit symmetry breaking here, some quark masses sitting here, or some energy. Yeah. Some M. What would be a nice guy explicitly breaking unitary symmetry invariant? Lowest order.
So you had some field.
A little mass, yeah, on the diagonals. What would you get? Plus, mass, or epsilon, energy, could be.
Sigma 3.
Time is running. No, there is no sigma 3.
No, you pick a particular matrix in the space that the unitaries operate on.
Yeah, I'm adding now here an explicitly symmetry breaking term. And I want to know what after expansion to lowest order, what do I get?
U times U.
Did I hear real part?
Yes.
Okay, yeah, it goes in the right direction. U plus U inverse. Yeah. Now there's a strange term you can add. C tilde trace U d U inverse and all that squared. But to lowest order and derivatives, that's it. Right. And I'm mentioning it for 3 reasons, maybe 2. First of all, this model has very interesting critical properties. Unlike, it doesn't behave like conventional sigma models. In the limit where epsilon goes to 0 in 2 dimensions, there is an interesting renormalization group flow. There is no localization, Anderson localization in the band center. Normal sigma models in the band center. And the density of states diverges in the band center. So there's something interesting going on, which I don't have the time to discuss. The keyword is Gade-Wigner. Gade-Wigner, early 90s. Another remark is when I mentioned this QCD analogy. In QCD, this piece here goes under the name Weinberg Lagrangian. That is a low energy Lagrangian of mesons. We discussed mesons are the Wilson modes, so there should be Lagrangian, and these are the quark masses. So in QCD, it has been around since the late 60s. We discussed. Huh? Yes. That's it. So let's keep that in mind. And what I would like to do my last still 10 minutes. Now I would like to confront you with another A3 symmetric system, which is very interesting because it is a platform of many theories that are under active discussion currently, and that's the two-dimensional Dirac operator. So what you can do is look at another Hamiltonian, Dirac. And now we get much better reasons for calling them left and right movers, because that's what they are, left and right moving bifermions. And so I have something like Py dot Px minus I Py, or another way of writing with P, what do they call them? I sigma I. Yeah? That's a clean Dirac operator in 2 dimensions. And it's A3 symmetric. Now let's look at this operator in a you can add disorder to this operator. And the disorder has now several options where it can couple. It can, for example, sit here on the diagonals. That would be, we would call it either random potential disorder if it's diagonal here, or if these are the same, or random mass, if disorder here minus disorder there. Or it couples here. If it couples here, then we go from H, then we obtain a Hamiltonian which has this structure, like P minus A is here, P dagger minus A dagger. So that is our disorder. It respects now the chiral symmetry and it couples like a vector potential. Yeah? So that is P I minus AI sigma I. This type of, now you can ask yourself what role will this disorder here play? And the answer is not much. Why? Maybe no?
We can make transformation to get rid of it.
Yes, you can gauge it out. You can gauge it out. So any observable that is gauge invariant will not couple to this disorder. So it should have a much lower effect than this model is seen here.
Is AI constant or is it?
No, it varies in space and time. So this is, we are in 2 + 0 dimensions. You can get rid of this now. There is a word of caution. If you gauge this order here, this is not an innocent gauge transformation because there is an axial anomaly. So when you gauge this disorder, you pick up an anomaly term, chiral anomaly or axial anomaly. But this anomaly will not talk to your observables as long as they are gauge invariant. So you don't have to worry too much about it. So that's what we know.
Is it the same being able to gauge your way as in 1 + 1 dimensional?
Yes, exactly. Yeah, when you do a functional bosonization, for example, you play this game. You could instead talk about the 1 + 1 dimensional interacting fermions, and you would have the same type of. Now let's forget that we can gauge it out and play our games. I mean, average on this one and so on, and we will run into very similar situations. We would have the symmetry breaking. We get our Goldstone modes, and then we would suspect we wind up here with this action. Oh, that was the lowest order action I was writing. And we would conclude that the disorder has a massive effect. So something is wrong. Any ideas what is wrong? Or what could be? I mean, it's an unfair question.
Some critical,
Huh?
some critical stuff.
Yeah.
You can't gauge out fluxes?
Huh?
You can't gauge out fluxes?
No, you can.
Are you going to get the topological terms?
Yeah. Topological terms, if you will. So there is, I said it's an unfair question, but this Hamiltonian here, there is another symmetry, unitary symmetry, which is broken by this Hamiltonian, and that's reflection symmetry, space reflection. Unitaries never played a role, but that here now they play a role. That's one of the reasons why I'm discussing it. So, I mean, on average, px to minus px and py stays the same, or something like that, is does not give this Hamiltonian invariant. In this action here, this action is symmetric under these transformations. I mean, space reflection. Huh?
Yeah, but you can't have just this Hamiltonian, right? It has a partner, which is the other valley. And
Oh yeah, no, that's just one valley. If I have two valleys, maybe my last half minute, yes, indeed. But this is one valley, you can think of it as a surface Hamiltonian topology. So we need a term here which should have a low number of derivatives and explicitly break this chiral symmetry, this reflection symmetry. And the solution is that for in the Dirac setting, you get, I mean, you go to this action here, this thing here, but there is a so-called Wessel-Witten term popping up for the fields U. And that one has two derivatives in it, and it breaks x to minus x. Now, in view of the time, I will not write this guy here. It's in the notes. I mean, you can see it. But let me just tell you what the story behind this term is. This action here, I mean, as it's written here, was first derived by or introduced by Witten in 1984 in the famous paper Non-Abelian Bosonization in 2 dimensions. So what Witten did, Witten looked at this operator here, I mean fermion operator, and you can think of it as 2 plus 0 dimensional operator or as 1 plus 1 dimensional fermions. Yeah? So we have 1 plus 1 dimensional fermions, but he was interested in a situation with several flavors. He didn't talk about this order. And he then showed that this fermion has a representation, a bosonic representation, much like what Thierry discussed with you, but in non-abelian version thereof. And the action of this non-abelian action, which is an analog of the abelian bosonized action, was this one here plus this, that one not, with a very particular term here, value 1 over 16 pi or something like that. And what he then showed is that this term plus that term is a conformally invariant package. So that's a conformally invariant theory. In fact, it's a free Dirac fermion. It has to be conformally invariant. But the conformal invariance here is very, very subtle. I mean, you do not get it for free. I mean, you have to work. Now, once you have this conformal invariant platform, you can show that if you now add this order, this constant here normalizes, and that one did, but these are marginal perturbations, so the theory doesn't care about this order, essentially. So the take-home message is that this was just an example, that symmetry classes is not all. There is, on top of this symmetry business, topology can sneak into the game. I mean, the Wessel-Witten term is a topological term. And this topology can be a massive intruder, can change everything at low energy. So that we have the same symmetry class, but two fundamentally different actions that happens. Yeah?
What this action with the Wessel-Witten term solved, or?
No, only RT. You can show that there is an infrared stable normalization fixed point. I think possibly one loop order. And there's something slightly better, but I forgot what it was. But yeah.
So I have a very stupid question. So this Hamiltonian is momentum dependent?
Well, it's what it is. It's derivative. I mean,
yes. Yeah. And so when you disorder average, you have sum over all momentums, or integrate over momentums.
It's just I mean, it's as in a Schrödinger operator. There is a momentum operator and a disorder operator.
There is a momentum as a quantum number, and I have to sum of all momentums.
You have to
It's a derivative.
So,
It's a derivative.
yes, it is. But in momentum basis, it's a quantum number, and I have to sum of all.
No. This order massively breaks. This order breaks this conservation of momentum.
Okay.
And but if that was the question, you're right that this is a trivial theory in the fermionic language,
Yes,
without this order,
right.
and it's very non-trivial in the bosonized language. So when you will not go to the bosonized language unless you have very good reasons to do that. But this is conformally invariant, and it's manifestly conformally invariant, and this one is also non-manifestly conformally invariant. Leo?
So for the same symmetry class, do you have many or more than one theories, depending on what topological number in front of topological term is?
It's yeah, more or less. I mean, you always have terms which, quote unquote, are metric dependent. I mean, like such gradient terms. And then on top of that, you may or may not have topological terms.
But can you have two physical systems? One has topological term and the other one does not, or?
Yeah, I showed you the sublattice system does not have a topological term. And the Dirac operator, which is in the same symmetry class, does have one.
Say it again?
The sublattice system and the Dirac operator are both in the chiral symmetry class A3.
Oh, I see.
And one has a Wessel-Minor term, the other one doesn't. And that's the only difference.
I see. So they behave very differently.
Yeah, absolutely different.
Even if there's universal limit and all
Yeah,
that.
yeah.
I see. But it's not like, okay, but it's either have it or not have it. It's not like there's different thetas that sit in front of topological.
No. That one has it and the other one doesn't. Because the topological term breaks symmetries, unitary symmetries, which the sublattice system has, and that pulls it out.
Yeah, maybe can I have before we finish a comment? John Jock also already mentioned that there are no derivative corrections to the conductance in this kind of class. So if anybody's interested, we have some recent progress on that. So we know where the localization to this comes from, and there's also numerical support for that.
That's with
Pasha
Ostrowski, yeah. This Costa-Litsaurus. Yeah, very nice paper, I recommend. Read it. Yeah.
In these two theories, one with this term and one without, are the spectral statistics different? Will those things?
What different?
Will the spectral statistics be different?
Spectral statistics. Now, spectral statistics, I mean, so far we discussed spectral statistics in zero-dimensional limits, where they collapse to the same. And, yes, they are.
They are.
Yes.
Even though the unitary time evolution manifold, those
yeah. There's additional modes you have here.
Okay.
Now maybe my time is up, I know, but there was a mentioning of two subvalleys, right? So this is precisely an example of what we had in the first lecture. When you say, and you have two graphene valleys, something like that. So here you have K and here K prime, right? And then here you have a little Dirac operator, and here you have a Dirac operator. And then you have again the situation we discussed. I mean, you have, if they are not coupled, then symmetries like time reversal in this reflection symmetry, in fact, get you from one island to the other. So you get the copy, the Wessel-Minor theory here, and another Wessel-Minor theory here, and they are enslaved. If you add now here something that scatters you from 1 to 1, you break